a 200 ms clock skew between data centers caused a write to be ignored, leading to 15 minutes of stale reads. Physical clocks are not reliable for distributed ordering. Here's why you need vector clocks instead. Welcome to TheCodeForge. Before we dig into that production issue, let's cover vector and Lamport clocks. Logical clocks replace physical time with counters. Each process maintains an integer that increments on every event. When a message is sent, the sender includes its counter. The receiver updates its counter to max, local, received, +1. This gives a partial order of events. Lamport clocks are simple. Each process has an integer counter. On send, increment and attach. On receive, set counter to max, local, received, +1. This gives a partial order, but equal timestamps don't mean concurrency. Here's a Java implementation of a Lamport clock. The tick method increments the counter before sending a message. The update method merges a received timestamp by taking the max and incrementing. Always use atomic integer for thread safety. Vector clocks extend Lamport clocks by maintaining a vector of counters, one per process. On send, increment own entry and send the whole vector. On receive, merge by taking element-wise max, then increment own entry. Now you can detect concurrency. If two vectors are incomparable, events are concurrent. This vector clock implementation uses a concurrent hash map to store only active entries. The tick method increments the local node's counter. The merge method takes element-wise max. The isBefore method checks causal ordering, and our concurrent detects conflicts. Use Lamport clocks when you only need total order, like a distributed log or mutex. Use vector clocks when you need to detect concurrent updates, like in CRDTs or conflict resolution. The rule of thumb: if you need to ask, did these two events happen concurrently? Use vector clocks. Here's a practical example: a shopping cart. With Lamport clocks, concurrent writes cause lost updates. With vector clocks, you detect concurrency and merge both additions. The decision depends on whether you can tolerate lost updates. Vector clocks can grow unboundedly if not pruned. Also, 32-bit counters overflow in high-throughput systems, causing events to appear out of order. Always use 64-bit counters, and validate received clocks to catch bugs. This pruning method removes entries that haven't been updated for a given age. But be careful, pruning too aggressively can lose causality information. Only prune entries for nodes known to be dead or removed. When vector clocks detect concurrent updates, don't use last write wins with physical timestamps. Instead, merge at the application level. For a shopping cart, merge items. For a key-value store, expose both versions to the client. This resolver returns the causally later value if one exists. If concurrent, it concatenates both values. In production, you'd store both versions and let the client resolve, like Ryuk does with siblings. This is the same issue we highlighted at the start. Here's exactly why that happened. The read repair logic used physical timestamps from clock get time. A clock skew of 200 ms between two data centers caused a write with a later physical time to be ignored because the read node's clock was ahead. The write's timestamp appeared in the past and was discarded. The fix was to replace physical timestamps with vector clocks per key. Each write increments the local node's counter. Reads compare vector clocks to ensure they see all causally prior writes. This eliminates reliance on wall clocks. This is the exact mistake from the incident. Using physical timestamps for ordering leads to stale reads when clocks drift. Always use logical clocks for distributed ordering. Vector clocks grow linearly with the number of nodes that touch a key. In a 1,000-node cluster, each vector clock is 1,000 integers. Without pruning, memory usage explodes. Periodically remove entries for nodes that haven't written recently. If you don't use atomic operations, your clock can decrease due to thread interleaving. This breaks causality. Always use atomic integer or similar monotonic counter. A 32-bit counter overflows at ~4 billion events. In a high-throughput system, that's days. Use 64-bit long counters to make overflow virtually impossible. The article mentions dotted version vectors, but doesn't show code. Here's a minimal DVV implementation that stores a per node, and a set of scene dots, reducing size when many nodes share the same counter. The code uses concurrent hashmap merge and integer, some method references which require Java 8 or later. If targeting older Java versions, replace with explicit put and get with synchronization. Always validate received vector clocks to prevent malicious or buggy nodes from corrupting causality. Check that all entries are non-negative and that the sender's own entry has increased monotonically. Reject clocks with negative values or huge jumps, e.g., 1e6, to avoid overflow or attack. To debug stale reads, first check that the read path merges the received vector clock. Use curl to send a request with a client clock. Then grep the logs for merge operations. Also check vector clock stats for size issues. Let's run through some common interview questions. How does a vector clock detect concurrent updates? Two clocks are concurrent if neither is less or equal to the other. When choose Lamport over vector, when only total order needed, e.g. distributed log. What happens on overflow? Counter wraps, events appear out of order. Mitigate with 64-bit counters. And a few frequently asked questions. Difference between Lamport and vector clocks. Lamport uses single integer, vector uses vector per process. When to use vector clocks, when you need to detect concurrent updates. Do vector clocks grow unboundedly? Yes, if not pruned. Mitigate with pruning and dotted version vectors. To recap, always use logical clocks instead of physical timestamps. Lamport clocks are cheap and simple for total order. Vector clocks give you full causality but require pruning. Use 64-bit counters to prevent overflow. Thanks for watching. Ready to go deeper? Up next, heartbeats and failure detection, then publish-subscribe pattern, then Kafka and the distributed log. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.